Welcome back to the School of Laboratory Medicine. This poetic presentation, the fourth one in the series, will take you through a very important concept in the clinical laboratory, namely bias. Bias is a concept which has its origins in the field of metrology, the science of measurements. Since a large percentage of reports generated in the lab are based upon measurements, understanding this term bias is very important. An unbiased view of bias, a poem that was published in the journal Clinical Chemistry in the year 2016. Bias is an important concept in the clinical laboratory scene. It is taken or considered to be the arithmetical difference between the mean of multiple measurements for a particular analyte against the result from a reference method considered as right. The inherent difference is what constitutes the systematic error. It may be quantified but is often difficult to eliminate altogether. The distribution of the results show a rise and a fall, with a peak in the middle showing the average of them all. The true value of the measurand is at a distance from the mean. This gap, representing the bias on the graph, can be easily seen. A Gaussian type of curve, typically taking the shape of a bell, is commonly used in metrology to illustrate this point very well. Bias may be constant throughout the measuring range if the difference between two methods does not change, whether the value lies close to the limit of detection or goes up as high as the upper limit of quantification. This constant error can be detected and quantified with ease, a correction factor added to the result before its release. If the bias varies with the concentration of the analyte, the situation appears slightly more complicated at first sight. The slope of the graph is what gets affected in this case. This curve deviates more and more as it moves from the base. This type of systematic error is referred to as a proportional one. It can be characterized better when a regression analysis is done. The concept of allowable bias is based upon the fact that analysts should be aware as to when they should act. Does the situation warrant a corrective action or does it not? This depends upon the biological variation values that we've got. The bias shall be well within inter-individual limits for a measurand if for the diagnosis of disease on this parameter we depend. A bias of 2% in the measurement of HbA1c is higher than the within individual variation, you'll agree. If superimposed on this bias is a component of imprecision, it could impact the clinical utility, leading to a flawed medical decision. By contrast, much higher bias could be tolerated without a loss of validity for measurands with large biological variations, such as the enzyme ALT. When a nephrologist scrutinizes the serial results of serum creatinine, or a cardiologist in the ICU looks at the values reported for troponin, the endocrinologist assumes that our ACTH reports are absolutely right, or the urologist takes at face value the PSA results at first sight. The physician thinks that saline infusion is what the patient needs. They rely upon the results we provide in thought word and deed. The testing cycle has several steps and processes. Each one could have its own impact. As Ishikawa's cause and effect chart illustrates this point exquisitely with figures and facts. Much like the diagrammatic representation of a fishbone, they could all integrate, causing their own positive or negative effects, errors they could propagate. Starting with patient preparation and ending with the report in the clinician's hand, there could be many a slip up with the patient or end user stranded in no man's land. It is time that we shed our biased attitude and tackle bias with zest and vigor. Keep a tab on deviations from the true value. Follow rules with greater rigor. To err is human, we all do know, but let's keep in mind the price we pay. The downstreaming effects could be catastrophic with human lives we play. Let us keep a vigil over the vital statistics of each and every method that we use. Into the land of quality with our sails unfurled, we would then easily cruise. We shall now turn our attention to the international standard. The standard meant for medical laboratories, which is known as ISO 15189-2012. The major clause 5.5 in this standard is about examination processes. The subclause 5.5.1.2 is about method verification, and the subclause 5.5.1.3 is about method validation. The laboratory needs to verify an examination procedure which the manufacturer has already validated. This is what the standard says. The standard explains in the note the meaning of the term performance characteristics. What are those performance characteristics that the lab needs to verify before the method is put to routine use for patient samples? It enlists the performance characteristics including measurement trueness, measurement accuracy, precision, specificity, so on and so forth. So we have to understand the concepts of trueness and inaccuracy and relate these to the term bias. Now let us look at the terms trueness, bias, and inaccuracy. The definition of the term trueness. Trueness is the closeness of agreement between the average of an infinite number of replicate measured quantity values and a reference quantity value. It is quantitatively expressed as bias, the gap between the mean of multiple measurements and the true value is bias. Bias and inaccuracy are often used synonymously. However, contemporary usage by ISO and CLSI makes a distinction between these two terms. Accuracy relates to how closely a single measurement agrees with the true value as shown in A, where n is equal to 1. Inaccuracy is the difference between the measured value, the single measured value, and the true value of the measurand. Now looking at bias again, bias relates to how an average of a series of measurements agrees with the true value as shown in the figure C, where the error is only due to bias. In the first case, imprecision contributes to the lack of agreement, whereas in the last case, imprecision is minimized, has been fully removed, ideally removed entirely because of the use of the average value. How do we estimate inaccuracy, and bias. The following methods are commonly used to estimate inaccuracy and bias. Inaccuracy could be obtained by participating in a PT program or a proficiency testing program or an external quality assurance program. Bias, on the other hand, could be estimated by comparison with a reference method or by using a certified reference material or by performing recovery experiments. Let us look at method A, by comparison with a reference method. A series of samples are run both by the candidate method, the method that is being tested, as well as by the reference method. The reference method is sometimes referred to as the gold standard method. The data is analyzed by plotting a graph, as shown in the diagram. The systematic error that is obtained could be either a constant one, as shown in figure A, or it could be a proportionate one, as shown in figure B. This error could be calculated and it could be introduced into the result of the measurement as a correction factor. If the two graphs overlap, unlike what has been shown in the figures, the bias is considered to be insignificant. Then we move on to the method B, the use of certified reference material. Certified reference material have a particular specific value. So by comparing the results obtained by the laboratory with what is written on the certified reference material, which is a true value, we can arrive at the bias. Method C, recovery experiments. By measuring the recovery of the measurand in spiked natural samples, the bias of the method could also be obtained. This is a numerical example of how bias can be determined in the lab. There are two samples of cholesterol shown in this example. In the first sample, the mean of 20 measurements as obtained by the lab method is 99.85 milligrams per dl. The mean of 20 measurements done on the second sample is 201.4 milligrams per dl. For the first sample, the true value for cholesterol as obtained by the reference method is 102 milligrams per dl. Therefore, the bias for the first sample is 102 minus 99.85, which is 2.15 milligrams per dl. Similarly, for the second sample, the bias is 205 minus 201.4, which is 3.6 milligrams per dl. So this is how the bias can be determined by comparison of the lab method with that of the result obtained from the reference method. We now have to look at the term allowable bias, which is taken as 1/4 of the square root of BVW squared plus BVB squared. So this is equal to 0.25 multiplied by the square root of 5.95 squared plus 15.3 squared, and this works out to 4.1%. This is a calculation based on biological variation. Biological variation, BV, can be BVW, which is within subject biological variation, and BVB, which is between subject biological variation. So this calculation is based upon the figures that we have got for biological variation both within and between human subjects. And in this case, the answer that we have got is 4.1%. Now this is referred to as the desirable allowable bias, and for cholesterol it is 4.1%. Now if you look at the table, the bias percentage that we have obtained from the previous experiment in the case of the first sample was 2.45%, and for the second sample it was 1.8%. Both these are less than the allowable bias, the allowable desirable bias. So this actually means that the method that was used for determination of cholesterol in the laboratory has a bias which is within the desirable bias. So it is an acceptable method and can be used for patient testing. The determination of bias could be done as part of method validation. In this slide, the bias has been shown for a number of routine chemistry parameters such as glucose, urea, creatinine, bilirubin, and enzymes such as amylase, alkaline phosphatase, lactate dehydrogenase, gamma glutamyl transpeptidase, aspartate transaminase, and alanine transaminase. The bias in this method has actually been performed by comparison of the results of QC samples. The new method has been compared with an established method. And the bias that has actually been obtained using the equipment known as cobas C501 has been compared with what is the allowed bias, the quality specification. Both of these have been represented in the form of a percentage. For example, the result obtained for bias on cobas for glucose was found to be 1.7. The quality specification for glucose is 2.2. Now let us look at urea. The bias obtained on the equipment was 4.4. The allowable bias is 5.5. Looking at AST, the bias obtained was 1.9%. The allowable bias is 5.4%. So the highlighted area shows that for all the parameters studied, the bias obtained on the control material, on the instrument, was lower than what was specified as allowable bias. Now let us look at the determination of inaccuracy by participation in external quality assurance programs or proficiency testing programs. The lab is provided with a set or a series of samples for analysis. The lab analyzes the samples at predetermined intervals, say monthly intervals for a period of say 1 year. The results are reported to the EQA or the PT provider. The laboratory gets an estimate of the mean of the results sent in by the participating laboratories. It also gets the extent of variation of results as standard deviation. It then gives the z-score or the standard deviation index, which is calculated as shown below. Your result minus the peer group mean, that is the difference between your result and the peer group result, is divided by the standard deviation of the peer group. And this gives the z-score or the standard deviation index. Let us look at a numerical example. The peer group has a mean of 46.7 millimoles per liter. The result obtained by the lab is 47.21 millimoles per liter. The z-score is equal to 47.21 minus 46.7, that is the result of the lab minus the peer group mean, divided by 1.57, and the answer is 0.29. This result is well within acceptable limits. Please note that this is a measure of accuracy, as the lab has analyzed the sample only once. So theoretically, it could have both systematic as well as random errors. Also, the mean has been derived from the results of many labs, and therefore it is the consensus value that is taken. Although this might be considered to be close to the true value, this is referred to as the consensus value. Some eco programs do provide the target values with which the calculations could be carried out. And now the take-home points. The terms bias and inaccuracy are often used interchangeably. Recent usage by ISO makes a distinction between the two. Accuracy. This is the closeness of the agreement between the result of a measurement and a true value of the measurand. Inaccuracy is the difference between the true value and the result of a single measurement. External quality assurance reports gives us the inaccuracy of our result as we measure the sample only once. This therefore could theoretically represent both the systematic as well as the random errors. Bias is the difference between an infinite number of measurements or the mean of multiple measurements and the true value of the measurand. So theoretically, this represents the systematic error. Bias may be constant throughout the measuring range, or it may be proportional to the concentration of the measurand. Bias needs to be quantified during method verification and method validation. This is as per the clauses 5.5.1.2, which talks about method verification, and the clause 5.5.1.3, which talks about method validation in the ISO standard 15189/2012. This can be done by comparison of the candidate method with a reference method. Allowable bias calculation is based upon biological variation within individuals and between individuals. The desirable value for bias should be less than 1/4 of the result obtained. Participation in external quality assurance programs provides us with the z-score, which is a measure of inaccuracy and represents both the random as well as the systematic error. Thank you for your patient listening. We look forward to seeing you again in our next session of the School of Medical Laboratory Sciences with another poem. Your feedback is solicited. Here is my email ID. Thanking you once again and hoping to see you soon.